Start. Hi everyone. Thank you for joining us for today's session. We have Panos here from DKRZ. Panos, go ahead.
Okay, thank you, Ofer. Hi, everyone. I will try to share my screen. So, can you see my presentation full screen?
Yes, we can see.
Okay. So, thank you, Ofer, for the introduction, and thanks for having me here. This is, for me, the first time participating in the student cluster competition. So I will start with a short introduction about DKRZ and myself. So I'm working at the German Climate Computing Center, which is located in Hamburg. You see here a picture of it. And Hamburg is also the place where the on-site ISC22 and the on-site cluster competition will be held this summer, provided COVID allows us. And the DKRZ is a dedicated computing center for climate science. This means that we have supercomputing systems in our institute, but all the work we do is focused on the needs of climate science, and no other users than those doing climate science can have resources here. And our focus is computer science and high performance computing, and not climate science. This is done by the Max Planck Institute for Meteorology and our other shareholders. And this is also my background. I started by studying computer science at the University of Patras in Greece, and following that, I did a PhD in mechanical engineering at the University of Stuttgart here in Germany, while I was working at the HLRS, which is the High Performance Computing Center at the University of Stuttgart. This doesn't mean that I am a mechanical engineer. It's just that the director of the HLRS, Michael Resch, holds a professorship in the Faculty of Mechanical Engineering at the university. So I had to do some exams and whatever was needed for the PhD in this department. Nevertheless, the focus of the HLRS is high performance computing, which has been since my studies and my whole career, also my up to now, my own working area, with a focus more on the software side and close to the application. So in HLRS, I was working with finite element programs, finite volume programs, simulating structural mechanics processes or thermal processes, or coupled or even computational fluid dynamics. And all of this with parallel programs and programming models like MPI or OpenMP. And I continued this work in December 2006 when I joined the DKRZ, but on the field of application now changed from the engineering applications towards climate science. So the heart of the algorithms and the methods and numerical methods is still the same. But the needs here and the demands for computational resources and efficient algorithms are much higher. So meanwhile, I'm leading the HPC software development group at DKRZ. Our focus is in the development of HPC-related software components and libraries for Earth system models, as well as optimization issues. So for instance, when we have to solve some problem on a model like ICON, we try to make out of it a library which could, so the solution we provide in a form of a library so that we can use this library also for other models. On one hand. On the other hand, certain type of optimizations, like for instance, GPU port of a climate component cannot be done in a very performance portable way. So we work with the models itself and use, for instance, OpenACC or OpenMP or whatever, but inside the model. So we have we follow these two paths. We work with the models themselves, and also with by developing our own library. So here are three of our current libraries. One is a coupler, which is used. The name is YAC, yet another coupler. This coupler is used to couple an atmosphere component to an ocean component. Actually, this is used also in the ICON version you have here in the cluster competition in your task. YACST is yet another exchange tool, and this library on top of MPI for convenient and efficient message passing interface communication. And a huge topic is I/O. Climate models produce lots of data. Our current file system has a capacity of, I think, about 50 petabyte, and it's full up to 96%. Our next file system will have 120 or 30, something like this, and I'm pretty sure this will be filled as well very, very quick. And so we have here developed together with colleagues from Max Planck Institute a parallel I/O library for the GRIP and NCDF formats, which are the formats used in climate science. Its name is CDI-PIO. Now, coming a little bit to the topic of climate science, I want to make a brief introduction here. So here you see what we mean when we talk about Earth system. So an Earth system has lots of components and many physical, chemical, and other processes which have to be taken into account. So first of all, from the sun comes the radiation, and this as it comes hits our planet, there are several processes going on in the atmosphere. Part of the radiation is being absorbed, part of it is reflected back to outer space. We have different interactions with radiation and the clouds. The radiation is responsible for heating up the ocean. So as you see here on the left, and the land, and because the ocean and the land are warmed differently, we have a temperature difference which causes wind. The wind then interacts with the ocean and affects the currents in the ocean. And so as you can see, this the whole Earth system is a very complicated system, and the software, so the model, the climate model, which is an implementation of the equations describing all of these processes, is very complex itself. Actually, the equations for this climate processes, or in this Earth system models, in the atmosphere and in the ocean, are not solvable analytically. So, and for this reason, scientists use numerical methods, which give an approximate solution using iterative numerical algorithms. And in order to do this, we have to use a so-called computational grid, which is something like the grid you see here on top of the land. Assume we want, so we lay this grid over the atmosphere, and now the partial differential equations are being transformed into algebraic equations, and now we can solve these equations in each of these boxes. And which means that the higher the resolution of the computational grid, or in other words, the more and smaller boxes I have, the better is my approximation and finally my solution. Now coming to ICON. ICON is such an Earth system model. The name, the acronym comes from icosahedral non-hydrostatic, and it is an Earth system model, which is a unified next generation global numerical weather prediction and climate modeling system. So it's the first time that you have one model for both, for numerical weather prediction, which is targeting rather short periods of time. You want to know the weather of today and the day after, but that's it. In climate science is defined as the statistic of the weather over a period at least of 30 years. So simulations, all the climate simulations have periods longer than 30 times, so 100 times, 100 years or so. And since we are talking about Earth system model, in addition to the atmosphere, the ICON model has also an ocean component and is designed to simulate multiple scales of the atmosphere and the ocean processes. One very useful feature of the ICON model is this local zoom function, which means that we can have different grids with different resolution, which can be nested one into another. So it's not an adaptive mesh refinement model where you during runtime or the model during runtime decides where to focus and do an adaptive refinement of the grid. No, the grids are statically defined at the beginning, but you can say, okay, I want to have a Corsa grid over the whole globe, and then go into focus into your region of interest by successively having finer grids nested one into inside the other, and then the equations are solved on all of these grids. So the solutions from the Corsa grid are then imposed as boundary or initial conditions for the next finer grid, and so on. And it's non-hydrostatic because it solves the compressible non-hydrostatic equations of motion, and by doing this, it allows us simulations at very high horizontal resolution. So this is how it looks like, and the grid is a result of the projection of an icosahedron. This is where the name icosahedral comes from. So if you project an icosahedron to the globe, then you will have 20 huge triangles, and these triangles are then successively refined by dissecting them, and then you can have grids with whatever resolution you like. On the picture here on the right, you see that we have this grid with the red triangles over the whole globe. And then the next level of refinement is this blue area, where we have the blue triangles. If you can see it very carefully, you will see that each red triangle consists now of 4 blue triangles. And then here over Europe, we have again each another step of refinement. So each blue triangle now consists of 4 black triangles. And this is how this local zoom function is working. But as I said, all of this is statically. You set up these grids at the beginning, and then you start the simulation, and no adaptive refinement is done during the computation, which means that, for instance, when you run it in parallel and you have domain decomposition done, this domain decomposition doesn't change, and we don't have load balancing issues or load imbalance due to different number of cells on each processor. The grids which are used are unstructured, which has some implication on the memory access patterns. And the whole code is written in Fortran 2003. There are some parts like the library for I/O, the CDIP I/O, which is written in C, but the model main computational numerical kernels are written in Fortran. The parallelization is hybrid, so we have MPI and OpenMP. Currently, this is work in process. There is a GPU port going on. The icon atmosphere, most of the parts or most of the atmosphere parts which are used in the experiments have been ported to GPUs with OpenACC. It has run in Switzerland on the pit stained. Now our port also to the Joules booster in Jülich has been done, and first experiments are ongoing there. The ocean part, we have done some first attempts only with one part, specifically the advection part, with OpenACC and with OpenMP. Now we have decided to continue with OpenACC the rest of the ocean. Where is ICON used? First of all, ICON as a numerical weather prediction model is used by the German Weather Service, so the DWD. It is in operational use for doing forecasts since January 2015, and also in several national and international research projects. The Swiss Weather Service, Meteo Swiss, will also use ICON very soon. I think the plan is 2023. Now the Swiss colleagues have acquired a new machine, which is also based on the GPUs, and so they will use the ICON atmosphere NWP part, which is already ported to GPUs to run there. Apart from this, coming now to the climate science area, ICON is used within the framework of the Intergovernmental Panel on Climate Change. You might have heard of it. It is the United Nations body for assessing the science related to climate change. You can follow their website. So here, this initiative contains a lot of research projects from different nations, different countries, and all have the same goal to assess how the climate change will be and how this is going to affect the conditions under which we are living on this earth. And it has a scientific part, but there is also a political part. So at the end, of this of each phase of these IPCC runs. There are as well scientific publications and a huge scientific report analyzing the new findings and results, but there is also a so-called assessment report for decision makers, which means that this is then going to politicians, and this report is also describing the impact of the climate change to society, or at least it tries to identify it. So what this is exactly, I will show you here better by showing you a video of one of the results. This is not done with ICON. This is an older result, but this is what they are doing in this IPCC runs. So you see here two Earths, which means that you will see two scenarios. The one you see here, RCP 2.6, this is an optimistic scenario, and this means that here the assumptions were made so that they assume the emissions on CO2 gases and other gases in the atmosphere, which cause increase in temperature, will decrease in the future, while on the right hand side we have this RCP 8.5 scenario, and here the assumption is that the emissions will continue to increase, which means that we do not do any change in the way we live. So as we are doing now, a life based on fossil fuels and whatever it means. And so the simulation starts in 1985. Here you will see the years go by, and here in this scale shows the difference in temperature, which means the temperature change. And now you see in how the temperature change is, and compare the two scenarios. Here the warming is much higher than here, and especially you will see that here the North Pole, the warming gets a maximum here. You see that is 10 to 11 degrees centigrade. This is, for instance, due to the so-called albedo effect, which basically says that since the melting of the ice is going on, the area of the North Pole decreases, which means that less radiation is going back, is reflected back, and so more heat radiation stays in the Earth, and so this increases the temperature change. So this sort of simulations are done for the IPCC, and meanwhile they have reached a point where they say, okay, we now doing different experiments with different models has shown that this increase in temperature, the global warming has to come, and now the next step is to be more precise and see what all of this means for what this means for us, for humanity, and how we can improve this climate simulations, making them more accurate. And within this IPCC initiative, there is this World Climate Research Program, and ICON is now used to do this coupled model in the comparison project, which is basically a project where they want to tackle three questions. How does the Earth system respond to forcing? What are the origins and consequences of systematic model BSS? And how can we assess future climate changes given climate variability, predictability, and uncertainties in the scenarios? And here you see, I just mentioned the atmosphere and the ocean, but the model itself, it's much more complicated. It has clouds, ocean, land, ice, land use, carbon cycles, chemistry. So the complexity of the model is very, very high in these projects. And in order to improve this and the quality of the projections, the climate projections, in one project, the HTCP squared, the aim was to also resolve the cloud and precipitation. And by doing so, the uncertainty in the climate change projections would be reduced by more than 50%. And this is a huge leap, I would say, in improving the quality of this climate simulations and projections, but it requires a lot of computational resources and software development. And we have done this in the HTCP squared project. And for the first time, instead of using parameterizations for the clouds, we went down here in the scales, the length scale, so below 1 kilometer, and tried to solve the equations at 600 meters, 300 and 150, but only at first time only over Germany. And now I will show you one of the results. You see here, clouds resolved simulation. This is the southwestern part of Germany. Here down you see the hours. It is a one-day simulation. And now you see here how wonderful the clouds are being formed. And you will soon see that the level of detail is so high that you can even calculate rain and also ice forming on top of the clouds, which is this pink surface here. Before HTCP squared, this was not possible, and the impact of the cloud system and the interaction with the radiation. And so this is the same now from the eastern part of Germany. And yes, the impact on the overall results of climate simulation is huge. And while we have done this and had very good results and everybody was satisfied, it turned out that this, although it was a first attempt, this research project, it turned out to be just an appetizer, because now every scientist wants to have this high resolution simulations for a global simulation over the whole planet, and to use them for large scale in time climate simulations, so that he can resolve small scale physical processes, and by doing so avoid the parameterizations which introduce some uncertainty and improve the climate simulations. This movie will shows a cloud resolving simulation, this time globally over the whole Earth. You see it here, flat Earth, and on the bottom left corner, you see the time and the days. The resolution is now 2.5 kilometer, but over the whole Earth. And again, you see very beautiful the formation of clouds, cloud water, and cloud ice. Now cloud ice is light blue, and you see here also some storms and hurricanes. So I wouldn't want to fly here, nor being on a ship in this region. And this is why we are doing all of these efforts of making the models more accurate. It's basically the question that, okay, now that we know that global warming is coming and nobody has doubts. Scientists the last 20, 30 years are working on this. By the way, last year, the Nobel Prize in Physics has been given also to two guys doing climate science. One's Klaus Hasselmann, who is the founding director of the Max Planck Institute of Meteorology and of DKRZ back in 1980s. And the other is Shiyokuro Manabe, if I pronounced his name correctly. And these two guys were awarded with a Nobel Prize for their methods in the work in understanding of complex systems. And so we can say that, okay, nobody has meanwhile doubts on it, but what's the next step? And the next step is we need accurate projections so that we can prepare society from natural hazards due to the climate change. And so tornadoes or droughts or floods mean climate change means also change in the sea level height, etc., is something which will come to us in the future, and we try herewith to prepare for it. Another project in which ICON is heavily involved is the Easyways Project. This is a European funded project, and it's for future exascale weather and climate simulations. So if you go to this website, there is a nice movie explains the Easyways efforts in 11 minutes. And basically, the question here or the aim here is at some point in Europe, we will have an exascale computer, and climate science at very high resolution, cloud storm and storm resolving simulations is one of the key applications we can use of such an exascale supercomputer. So right now, the most powerful computer is too small for what is aimed in this project. And for this, we are doing in the framework of this project further developments to make ICON fully capable of doing storm resolving resolutions. And these films are also on YouTube. You can watch them whenever you want. Now here you see the same, but now on the Earth as it is, so as a sphere and not flat. So we start with a 5-kilometer resolved grid, and you see that even this grid is so fine that you can here calculate, and if you want, yes, predict how hurricanes, storms, whatever other weather extremes are being formed. Watch this guy and this guy. This has already hit the East Coast and moves upwards. I'm sure that people living here would want to know this many days or weeks ago before it hits them. Now we go, we zoom in, we increase the resolution, and you see that now much more finer structures here can be seen. Meanwhile, I guess you are experts in cloud. You see, you know what is cloud, what is the blue, which is the white color, the blue color is the rain. And now I stopped the film just to show you that now we have left the global resolution, and we go now to local domains, and now the calculations are done are focused only on this rectangle here. And you will see that now we are at 1.25 kilometer only on this domain locally. Now we zoom into 600, 300, and you see the rectangle is becoming smaller and smaller. By the way, this year is Barbados, and here there exist also a lot of measurement instruments who do several measurements with LiDARs and other equipment in the atmosphere, with which then the model results are compared and validated. And so although this is a very nice movie showing what we want to do, this has not been done in one simulation in a row. But these were several resolutions, several experiments glued together for the simulation. What we want to do at the end is to have both global high resolution simulations in the atmosphere, but also in the ocean, and then also couple them. So now I will show you some results of a project called Sub-Mesoscale Telescope project. And here with the ICON ocean model, the Gulf Stream and the eddy currents in it are being simulated. And you see here that the name is telescope because the resolution of the grids start at 11 kilometers, but are constantly refined up to 550 meters. So now we are talking about meters, not kilometers. And you will see how what fine structures you can simulate with this. So at first glance, what you see is nothing. So you hardly see any movement. Now I've stopped it. Here, this is where we are interested in, and we don't see any movement. And when we did this the first time, I was a little bit worried. But Niklas Röber, our visualization guy, then told me this is not because the model didn't do its work properly. It's because the resolution is so high of our calculation and the grid, but the resolution of my screen is not so high, and I can't see them. And so when moving in, like Niklas did here, zooming in, and also applying some visualization techniques and tricks to visualize the whole velocity and how the masses, water masses are moving, or this Q criterion, for instance, technique, which is one technique for detecting and identifying vortices in a flow field. You can see how powerful everything is, which brought us to the next great or grand challenge. That okay, on one hand, it is a great challenge to do all these simulations, but after having these simulations, we have another challenge: how to analyze and to visualize them. So Niklas, who has done all of this terrific work in the visualization, is meanwhile working for NVIDIA. So I hope maybe in the next years, NVIDIA and Niklas come up with more fancy tools to be used in this high resolution simulation, which is the way we will go. And I'm sure we will go. Right now, we say that our goal in Easyways is to have a coupled atmosphere ocean simulation, both at 1 kilometer resolution, and the performance of the simulation should be one simulated here per day. This means that in one real calendar day, so in 24 hours wall clock time, we should be able to simulate one model year, because this is the performance the climate scientists need, because they need to perform many experiments, so up to 100 model years, and repeat them with different initial and boundary conditions to do the assessment. And so this is the target they have given us to achieve. If we can achieve this on the next exascale system, would be terrific. Currently on our Mistral cluster, which is a peta scale system, 3 petaflops, we can run not 1 kilometer, but a 10 kilometer coupled ocean atmosphere simulation with this performance. So we have on 1,600 nodes, we Broadwell nodes, so we have one simulated here per day. But in Easyways, we want to have this performance with a 1 kilometer resolution. And as an appetizer, this is the next film shows a whole year, 1 year of simulation at 5 kilometers. And so here on the bottom left, again, you see the days, the hours, the months. And now we have here a coupled simulation, which means in this results, all the interaction between the ocean and the atmosphere has been taken into account. You see the temperature on the land, on the sea surface, the wind at 10 meters with different ways of visualizing. So we have many information on one picture, on one movie, and now we have also the sea surface height, and together with the temperature over the land. The temperature is changing rapidly because, as you see on the bottom left, the days are moving very fast for the sake of the just showing this video. Now we have our sea, the currents inside the seas included. Again, when you see something not moving like this here, it's because of the resolution of my screen and not of the resolution the model calculations are being done. Ocean salinity and precipitation, all of these are very important to see. For instance, when you are a mayor or some authority, you are interested in when you live near the coast, you want to know when the sea level will rise and how much it will be, so as to see will your village or city still be on land, or will it be under the sea, so as to move away from there, the people. And with visualization techniques and data analytics techniques, AI is one of it, which we are also following. Is it possible then for the scientists to do the assessment? So here you see one plant's different things which you have seen before. And this just shows how powerful this high-resolution simulations with ICON are, and how important they are for the future. So now this will not change, and I will stop it here. So now that we know our goal, we can I can come briefly to the task for the student cluster competition. So you will basically use the same version, ICON version, with which these coupled simulations have been done. The only difference is that the experiment you will be running is on a much coarser resolutions than this kilometer scale, because you have to run this on 4 nodes, the maximum, and it should take no longer than 30 minutes. So we have the ocean has a resolution of 100, and the atmosphere has a resolution of 158 kilometers, and the ocean of 360 kilometers. And I run this model many times, over 50 times, on 4 nodes on our old I have to say, still cluster Mistral equipped with a Broadwell processor, so 36 inside one node, and the wall clock time was 30 minutes for one simulated year. So now your goal is to speed up the execution time for this experiment. The data have been made available to you. And of course, you have to port and tune the icon model to the new architecture of Niagara and the Bridges 2 cluster. So this is basically the same task the benchmarkers of the vendors, whenever we go to a procurement, are doing. So we are giving them some reference runs, results, and timings, and then they try to make icon run faster by tuning them to the architecture they are aiming to provide us. And so when the first thing you do is you have a different processor architecture. So my reference runs are done on Broadwell, which is very old. Now you have a Skylake and AMD EPIC Milan, I think. Correct me, Ophir. So I'm sure that you will want to try different compiler options, libraries like MKL or MPI libraries or whatever. This is one thing that you can do. On the wiki, I have also provided some tuning parameter from model side. This is this nproma parameter in the run scripts. And this nproma can help you improving the vectorization of the model, because this nproma is say defining the length of the innermost loop of all the computational kernels in ICON. So in Fortran, it is also the first dimension of the arrays, because Fortran has column-centric memory mapping. And you can try this especially in conjunction with options like AVX2 or AVX512. Another issue that you will face is load balancing. So we have two components running here, the ICON atmospheric and the ICON ocean part. And in my reference runs, I had given 3 nodes to the atmosphere and 1 to the ocean. And with this, I could manage to run this 1 year within the given 30 minutes. So you, in the wiki, again, I have given some instructions how this can be analyzed and also changed. So you have some parameters in the scripts where you can use to do your own process placement, so as to say. And the last thing is I would like to have a profiling analysis, especially for the MPI communication. And if you could identify the bottlenecks and write them in this analysis report, would be extremely helpful for us, because if you see in the timers report given by ICON, we have own timers put inside there, but for communication, we have one covering the whole communication. So it's called exchange data. So if so this is it here. If you can see it, exchange data and exchange data weight. But this is covering all MPI calls. So it would be good if by using some tool like this IPM, which is a very low overhead profiling tool, if you could give your own view on the communication patterns we use there, and maybe suggest what we could do better. The last thing I want to say here is that I tried other tools, especially Vampire or Score-P, which I like very much, but they produce a very huge overhead. And this is why we couldn't use them. So they are collecting so many information, and the buffers are filled very quickly, so that we hardly can do simulation of not only a year, not even some hours. And by the way, if you encounter problems, similar problems with the IPM, please contact me immediately. We can reduce, for the sake of the analysis, the simulation time. And it is better not to waste your own time looking upon how to do it. Tell us, and we can show you how to do it, and so your work will be faster. Whatever you do, any optimization in the communication and the load balancing or processor specific, you have to check the results for correctness. And for this, we have given you a Python script, which you can use in Jupyter Hub. And after you run it, the instructions are in the wiki. You will see these two plots. So this is the global mean temperature at 2 meters, and the actual run is the red line. And these gray lines in the background, these are the reference runs which we made at DKRZ. So your line should be following the same shape. Let's say it doesn't have to be exactly the same, but it should be here. And if the deviation is too much, we cannot accept this as correct result. If you see you have slight differences here, just send us the result and we will tell you whether it is acceptable or not. At the same time, we have here this line, this total salinity or salt in from the ocean. This has to be completely identical, and this is the reason why you see only here the red line, and the gray line is totally covered by the red line. So if you have here any change, then the result is totally wrong and cannot be accepted. And just for your orientation to see what you are calculating with this experiment, is you are calculating here this the surface temperature in Kelvin at the 2 meters height from the surface. And here these two plots just show you the difference, the absolute difference, and the difference in standard deviation from the reference runs we prepared for comparison, and the same here for precipitation. That's what you have calculated, or what your experiment will calculate, and this is how the distribution of the difference in precipitation from the reference runs in absolute and in standard deviation. And at this point, I would like to thank you for your attention. I hope I didn't scare you too much. I intended to motivate you to work with ICON. And so now I'm available for questions.
So if anyone have any question, any comments, just feel free to ask. There's a few updates on my side. We have the input file. It's an 8 gigabyte input file on both Niagara and Bridges 2. You all supposed to have access now to Bridges 2. If you don't, let me know. They opened your users, the users you supply to us. And I added on the icon post on the wiki page how to copy the input from David's David's account. Besides that, we always have the Slack channel, which is open. You can always email us any questions that you have, anything that you encounter. Feel free to let us know. And that's it. Any additional, any questions? You know, don't be shy. Any feedback? I can say that I personally enjoyed the presentation. It's always amazes me how hard it is, you know, to add in one simulation, on a few simulations, all the differences between the different models. I mean, the atmosphere, the ocean, the air, the space, everything interact with each other in different locations, and it's still very hard. So still it's very hard to predict more than a few days ahead for specific weather, but it's better than you know, it was I don't know, 20, 30 years ago on the predictions. So we are you know, we are doing better jobs, but it's still the, I would say, chaotic way that the convergence of the models, I would say, right? It's hard to predict too long ago, right? But yes, the global warming is affecting us, and those things are very important to understand, and maybe hopefully influence governments around the world to make their changes to save our planet. So
I see one question here.
yeah.
No, it is not required to run a GPU instance. So if since only the icon atmosphere or parts of it have been ported to GPUs, and we are interested in coupled, we didn't require. We thought that we require only CPU runs because we are interested in this, in tuning this coupled setup.
Okay. Yeah, okay. If no question, that's okay. You know, question, maybe you didn't start at, you know, so much to dive in details. In general, if you have any questions, just feel free to contact us. We'll try to support you. And Panos, I would like to thank you for the time, for the presentation, and for the whole support in the competition. Just another reminder, we have next week, we have 2 additional presentations, one for the InCompact 3D and the other one for the coding challenge. And the next week, on Monday in 2 weeks, we will have our formal opening ceremony. So we'll hope to see you there. And formally we'll start the competition, the online part. Okay, so thank you very much everyone for joining, and we'll see you next week on our next session. Thank you, Panos.
Thanks for having me. Bye-bye.
Bye-bye.